Okay, are you there? Can we start now? Okay. So we were talking about cyclic conjugated hydrocarbon, which is nothing but annulenes. Okay. Like for this example, you see the name of this compound, general name will write annuline, and in the bracket we write a number which is equals to the number of carbon atom in the ring. Okay. So this number should be equals to the number of carbon atom in the ring. Okay. So this is an anti-aromatic compound because it has 4 pi electron. So anti-aromatic, we have already discussed this. Similarly, benzene is also a type of annuline, and the name of this compound is annuline 6. Right? So these compounds we already know it is aromatic compound, 6 pi electron. This compound, the name of this compound is aniline 8 because there are 8 carbon atoms. Aniline 8. Okay. And number of pi electron, if you see, it has 8 pi electrons. 8 pi electrons. Expected to be what? Expected to be anti-aromatic. Expected, right? But since the carbon atom is more than 7, then the actual property is what? It is non-aromatic in nature. Right? Non-planar. It is non-planar, changes its plane and becomes non-aromatic. Okay? So this one is expected but not true. Okay? The structure of this, if you see, which is not actually important, but I'll just draw here. This structure. 1, 2, 3. Like this, it changes its plane. Okay? And becomes non-aromatic. Okay? One very important example we have here in aniline, which is this structure. Okay? Now in this structure, what happens? Right? If you count the number of pi electrons, the name of this compound is what? It is aniline 10. 10 carbon, 1, 2, 3, 4, 5, 6, 10. Aniline 10. Okay. The number of pi electrons, if you see, it has 10 pi electron, right? And hence expected to be aromatic. Okay. But what actually happens here, this hydrogen, because this carbon is sp2 hybridized, so we must have one hydrogen present this side, and here also one hydrogen present this side. This distance is not that enough so that it can accommodate two hydrogen atom over here, right? So because of this hydrogen hydrogen repulsion, one of the ring comes out of the plane. Okay, one of the ring comes out of the plane, and the because of this hindrance, I'll write down, because of this hindrance, molecule becomes non-planar. Is non-planar. To minimize the hindrance, it changes the plane and becomes non-planar. And when it is non-planar, it cannot be aromatic, but it is what? Non-aromatic in nature. Okay. So this kind of compound is non-aromatic. If I write down this example, similar kind of example we have. Right. This example. And here what happens with this bond and this bond, Suppose some another atom is attached, this is oxygen. Right? These two means this oxygen is coming towards you. It's this the whole ring is in one plane, and this is coming above, like it is at the upper surface of the plane, coming out of the plane, right? So this bond, if it is any atoms attached like this, then this ring, which is this ring, is planar, and the molecule is aromatic in that case. But if any atom is not attached like this, we have hydrogen hydrogen repulsion here, and then the molecules becomes non-planar, then it is non-aromatic. These are few examples which you have to keep in mind. Okay, normal logic if you apply, you will get wrong answer. Okay, that's why I'm telling you that these examples you must revise before going into the exam. Okay, one last example we'll see. The compound like this. This compound. Number of pi bonds, if you count here, 1, 2, 3. Only one pi bond will count here, 4, 5, and 6. So we have 6 pi bonds, 12 pi electron. The 12 pi electrons means what? It should be anti-aromatic. But again, number of carbon atom is more than 7. So anti-aromatic is not possible. Molecule is non-planar and it is non-aromatic in nature. This one, this one. Nothing. You see here what? If you have hydrogen, hydrogen like this, okay, if you have hydrogen, hydrogen here present in the same plane of this ring, then we have hydrogen, hydrogen repulsion, which because of that, one of the molecule will come, one of the ring will come out of the plane actually. Okay, one of the molecule will come out of the plane to minimize the repulsion. Okay, and that is how one hydrogen come this side and another hydrogen will go away from you. It's like that. Okay, uh, because of the repulsion here, to minimize the repulsion. Now in this process, the whole molecule as a whole, this pi electrons are not in conjugation with these pi electrons, and hence it becomes non-aromatic, correct? But this, if one oxygen or any atom attached with this two carbon here, and this bond is coming above this plane, right? This oxygen is somewhere here on the top, right? The whole molecule is in one plane. This whole molecule is in one plane, and this two carbon is attached with oxygen, which is present above this plane here, right? So in this case, this molecule is planar and hence aromatic. Understood? So these are the examples you should keep in mind for aromaticity. You must revise all these examples before going into the exam. If any question they ask from this aromatic part, you will be easily answerable to those questions. Okay, you can easily answer those questions if you remember all these 2 3 conditions in mind. Okay, can we move on next? Yeah, can we move on? Yeah. So next you see, we are going to discuss next is hyperconjugation. We'll discuss hyperconjugation first because this application is also required there for hydrogenation and combustion. So hyperconjugation will finish quickly, and then we'll start hydrogenation and combination if the time permits today. Okay. Otherwise, we'll finish this into the next class. Okay. So you see, hyperconjugation, we also call it as, last class also I told you that it is sigma pi resonance because sigma converts into pi, or we also call it as no bond resonance. Hyperconjugation is only possible in case of alkene, alkyne, alkene or alkyne, in case of carbocation, and the last possibility we have in case of free radical. Carbanion does not show hyperconjugation. Okay. Hyperconjugative structures are what? For carbocation, you see, if I draw this structure, suppose we have CH2, CH3, CH double bond. So for hyperconjugation, the condition is what? We must require sp3 hybridized alpha hydrogen, right? At alpha position, we must have sp3 hybridized hydrogen present. Okay. So what happens because of this? You see, this sigma converts into pi, and this pi converts into lone pair here. The hyperconjugative structure of this will be CH2. This hydrogen will present here as H plus only. Double bond CH, single bond CH2, lone pair, negative charge. Right? See, since sigma converts into pi, that's why we call it as sigma pi resonance. And since H plus is present there without any bond, hence we call it as no bond resonance. Okay. Now this structure you can draw with the other two hydrogen also, right? So the other two hydrogen with also you can draw the structure. You'll get similar kind of structure, and that structure I am not drawing. Okay. But these three structures are, we call it as hyperconjugative structure. Hyperconjugative structures, right? So if they ask you how many hyperconjugative structure we have, you just have to count the number of alpha hydrogen, right? Number of hyperconjugative structure is equal to the number of alpha hydrogen present over there. Number of, if they ask you the total number of structure, total structure possible, that will be equals to the number of alpha hydrogen plus the given structure, this structure also. This 3 plus this is the total number of structure possible. Correct? Other thing is what? More number of alpha hydrogen, more hyperconjugative structure you can draw, and more will be the stability. Got it? More will be the stability. So the one factor we'll understand here, that stability of alkene also affected by hyperconjugation. Stability of alkene. And this stability is directly proportional to the number of alpha hydrogen present. Right? Number of alpha hydrogen present. For example, you see, first question, compare the stability of these alkenes. Double bond, this, stability of these alkenes. A, B, C, D. Which one is most stable? Tell me. The first one, number of alpha hydrogen here. How many alpha hydrogen we have here? 3, 3, 6, 9, 12 alpha hydrogen. The number of alpha hydrogen here will be 9. The number of alpha hydrogen here 6. Number of alpha hydrogen here is 3. More number of alpha hydrogen, more hyperconjugative structure you can draw, and hence the stability will be this is the most stable compound, and then this, and then this. Right? Number of alpha hydrogen, if you count here, it will be what? These are the alpha carbon 1, 2, 3, 4. 4 alpha carbon with 2 hydrogen on each. So we have 8, and number of alpha hydrogen here will be 1, 2, right? So 1 and 2, 3, right? So number of alpha hydrogen is more here, more will be the stability. Number of alpha hydrogen, if you count here, 3, 5, 7. Number of alpha hydrogen you count here, that will be 1. So this one is more stable than the first one. How many alpha hydrogen we have here? And how many alpha hydrogen we have here? Where we have 9. See, here the number of alpha hydrogen is what? 3 here and 3 here, 6. This is the alpha carbon, right? Number of alpha hydrogen 2 here. Stability will be this. Yes. What about the stability of this molecule? Stability of these two? Why equal? Second one is more stable. Why? Because second one has more alpha hydrogen. Okay. You see, here what happens? We have resonance possible, conjugated system. Here we have hyperconjugation possible. Resonance is more dominating. Stability order is this. So the order of stability follows this thing: R, H, and then I. If we have two molecules given, in one we have resonance, other one we have hyperconjugation, then the resonance one is more stable. Okay. Similarly, tell me the stability of this alkene. OCS3, then CS3. Which one is more stable here? A or B? All these things requires to solve the questions which is related to heat of hydrogenation, heat of combustion. Because heat of hydrogenation and heat of combustion depends upon the stability of alkene. So first of all, you should know the stability of alkene. And to stability of alkene, to explain that, you should know what is resonance, what is hyperconjugation, what is high I effect, how it affects the stability of alkene. Okay, how will compare the stability of alkene there, right? So here we have lone pair present on this, right? So this lone pair is involved in resonance here, right? That is why this one, and here we have 3 alpha hydrogen, number of alpha hydrogen are 3, and here we have resonance, correct? And this is hyperconjugation. Okay, so this one is more stable here because of resonance, right? So when you have this order, or if you can identify the resonance and hyperconjugation, you can find out the stability, and with that we can compare the heat of hydrogenation and combustion also. See, in all these examples, first 4 examples that I have given you here, you see, the first 4 examples that I have given here, in all these examples, the number of alpha hydrogens are different, right? Number of alpha hydrogen are different. But what happens if the number of alpha hydrogen are same in the given compound? For example, if I give you this example, suppose we have CH3, C double bond, CH2, CH3. This is one compound. And the another compound is this CH3, C double bond, CCH3, H, H. And the last one we have is CH3, CH double bond, CH, CH3. Okay. In these 3 molecules, we have to assign the stability of the alkene. So if you count the number of alpha hydrogen sp3 hybridized, right? So here it will be 3 and 3, 6. Number of alpha hydrogen here, if you see, 3 here and 3 here, 6. Number of alpha hydrogen here it is 6. Right? Now, so which one is more stable? That's the question. So now when we have number of alpha hydrogens same, so what we do, we'll try to write down the hyperconjugative structure. For this, if you write down the hyperconjugative structure, that will be CH2 double bond C single bond CH2, right? Negative charge. One CH3 will be as it is, and we'll have H plus present here. Correct. Further, this kind of, you know, 5-mode structure we can draw. Yes or no? Are you getting it? Let me know, guys, please. 5-mode structures will get similar kind of structure, right? If you draw the hyperconjugative structure here, that will be CH2 H plus here, double bond C, single bond CH, negative charge CH3, and H also we have, right? And similar kind of 5-mode structure again we can draw. Okay. Similarly, here also if you draw the hyperconjugative structure, that will be H plus CH2 double bond CH single bond CH CH3. Similar kind of again 5 more structure we can draw. Now, what is the difference in these three hyperconjugative structure? Can you tell me the difference here? What is the difference in these three hyperconjugative structure? No, no, Kushal. Hyperconjugation. What is the difference here in these three structures? Tell me. See, this structure is, it is 1 degree anion. Yes, it is 1 degree anion, right? This is 2 degree anion, and this is also 2 degree anion, right? And we know 1 degree anion is most stable. So the 5 more structure that you draw here, all the structure will give you 1 degree anion only. And that is why this is, suppose A, it is B, and this is C. So one thing we are sure with, that A will be the most stable alkene. Since in all the hyperconjugative structure, we are getting only 1 degree anion. Here you see, in this too you can apply some steric hindrance factor, right? Since both the methyl group are at maximum distance and both are 2 degree anion, so because of this more distance, the hindrance will be less, and hence B will be more stable than C. Anyways, trans isomer is more stable than the cis one. So these two you can say easily. This is trans, this is cis, sorry, this is, yeah, trans and cis, this one is more stable. And since this one gives you 1 degree anion, so this one is the most stable compound. Did you get this? Okay. Now after this we can discuss heat of hydrogenation. Okay, but we don't have time for that. Okay, so we'll start heat of hydrogenation in the next class. I'll take probably, uh, 1 hour more to complete this heat of hydrogenation combination combustion, and then we can start discussing problems, right? Problems on this. One more thing we'll discuss. You know what is SIR effect, SIP effect? You know that steric inhibition of resonance. How ortho substituted benzoic acid becomes more acidic than the para or meta substituted. Why it happens? You know that. Okay, so next class in first 1 hour, right? We'll finish all these things. Okay, hydrogenation, combustion order, how to define, and then some acidic basic nature also. What all effects possible at different places, and how ortho substituted benzoic acid is more acidic than para or meta substituted. It takes time. Okay, so we'll discuss this into the next class. So all of you must revise whatever we have done today. Okay. Aromatic compounds examples, you just keep those examples in mind. You won't get anything more than that. Yeah, I will send you. I will send you a worksheet on that. One PDF file I will send you. Okay, today only I will send. Okay. So we'll wind up the class here. Okay. Thank you. Yeah, I'll send you the worksheet today. I have one few set of questions which involves JE mains question only. That also I'll send you, and there are a few basic questions also I'll send you. Because there are totally 30, 40 questions will be there. Okay, so we'll send you that. Okay, thank you guys. We'll see you in the next class. Take care. Bye bye.